In truth, this is not just a Feigenbaum fest or an Ed fest, but a celebration of all of you and all the remarkable things you have done and are still doing. These are things that change the world. If we don't understand what it is that made us excellent, then we don't know enough to keep ourselves being excellent over time. I think of what all of you have collectively done. You built the first expert system, and later the first conversational interactive expert system, and then the first and second of the expert system development software tools. And then you were entrepreneurs in the knowledge industry.
Ed Feigenbaum's contributions to computer science are many. They are all part of a steadfast vision to make knowledge-based systems real and useful. More than any other person in the history of computing, Ed is identified with the simple phrase, knowledge is power.
I can't complain too much because I think I have gotten some of the best advice about how to be a writer and a communicator from Ed.
And in fact, I got more advice on the thesis from Ed and Bill than John McCarthy.
He established a strong base, and he's passed on the lineage. He's been an inspiration, a conveyor of values, and a towering figure. And thank you, Ed.
In 2006, a group of scientists, colleagues, and friends gathered at Stanford University for a 70th birthday symposium to celebrate the contributions of one of the most influential 20th century computer scientists, Edward Feigenbaum. He is known in computer science as the father of expert systems. He won the 1994 ACM Turing Award for basic and applied research in artificial intelligence that changed the way we view intelligence in people and computer software.
Well, this is about Ed Feigenbaum, the person. We'll hear a lot about Ed Feigenbaum's contributions to science and to many things. He has his name on the birth certificate of knowledge engineering and more.
One of the things that impressed me the most all these years that has stuck with me and has in effect shaped the researcher that I became is advice Ed gave me when I was a graduate student, which was you only have a limited number of decade-sized research bets to make in your life. Make each one of them count.
In my view, the thing that we call AI, or that maybe is better called computational intelligence, computers doing intelligent things, is the manifest destiny of computer science. That is the end of the road. When we finish our job, we will have invented the ultra-intelligent computer. That's what we're trying to do, whether it's 100 years from now or 200 years from now, but that's what we're trying to do. For reasons that are not totally clear to me, I really, really wanted smart machines.
Born on January 20th, 1936, Ed showed an early aptitude with calculators.
My stepfather was an accountant by trade, and he would bring home a lot of work. And he would do it at home on one of these mechanical calculators. And I learned to really know how to use that machine, and I was very proud of it. I would show it to my friends. And therefore, I kind of had a bias toward being interested in calculating machines. So here I am in New Jersey, on the Palisades overlooking New York City, a high school which was an academic-oriented high school. I happened to see an advertisement for the Carnegie Institute of Technology, and so since I really needed money to go to school, I applied for one of those scholarships.
While an undergraduate of electrical engineering at Carnegie Tech in the mid-1950s, Feigenbaum discovered behavioral science and the problems of modeling human behavior.
So I asked my advisor if I could do something else, and I looked through the catalog and I found a really interesting listing called Ideas in Social Change. Wow. Except it was being taught at a place I never heard of, which was on the other side of campus, called the Graduate School of Industrial Administration. My advisor said, sure, go ahead and see, and March let me into the course, even though I was an undergraduate.
While an undergraduate in electrical engineering at Carnegie Tech in the mid-1950s, Feigenbaum discovered behavioral science and the problems of modeling human behavior. His mentor and guide was Herbert Simon, one of the most influential behavioral scientists of the 20th century and 1978 winner of the Nobel Prize in Economics. Ed discovered computers and AI. He found his calling.
So Simon was teaching these modeling methods and modeling motivations, techniques and so on to this small group of students. That was the particular class that I tell the famous story about, where Herb Simon comes in and says, over Christmas, Alan Newell and I invented a thinking machine. And he handed us an IBM 701 manual, an early IBM vacuum tube computer. It was their first commercial binary computer product. That was a born-again experience. That was taking that manual home, reading it all night long. By the dawn, I was a born-again, or I shouldn't say born-again, just I was just hooked on computers.
I want to start with an Ed story, and I'm not sure whether this actually happened or I just remember. I remember Ed coming. It was about 1963 to MIT, and describing Epam to all of us. And I thought this was amazing, a symbolic model that would describe how people actually work.
Ed's first effort was modeling how simple acts of human memory and recognition were done. His computer model was called Epam, for Elementary Perceiver and Memorizer. Over several years, Feigenbaum and Simon extended Epam into a robust theory of learning and memory, a theory given form as a computer program.
So I got back in September of 1956, start the new year, and I walk into Herb Simon's office, say, I'm here, I have this fellowship, and what do I do? And he opens up an issue of, the current issue of Scientific American, or maybe the issue before last or something like that, and he shows me an article about human learning.
Simon was interested in the serial positioning effect, which described man's ability to remember items at the beginning and ends of randomized lists. Epam explained a wide variety of well-known experimental results in the psychology of verbal learning. Remarkably, it also revealed a basic mechanism for forgetting as a consequence of learning.
And Simon said, okay, let's make sense of this. Here's the data. This is elementary learning. We can't ask for anything simpler than this. This doesn't have meaning associated with it. It must have something to do with memory structures. Let's see if we can construct an information processing model, basically as simple as we can, to explain this data. By explain, he meant numerically explain, predict these numbers that the psychologists were felt were stabilized numbers. That is, they would talk about them in terms of something like the serial position curve was a real curve. It had real numbers at each end, and it varied with the meaningfulness of the syllables, and never, ever was the brain brought up. This was totally a model of mind, a model of human information processing with symbols at the lowest levels.
When I first got to know Ed, I came to realize we were dealing with a closet philosopher. Part of Ed's fascination, I think, with the process of science and philosophy of science came about through the stories you've heard. And at Berkeley, he was fortunate enough at the business school to make the acquaintance of Wes Churchman, who was one of the founders of Operations Research, but a very empirical person who was himself much interested in the scientific process.
If you're the supervisor of a graduate student, one of your responsibilities is to help place the graduate student in a proper job, hopefully academic job, down somewhere. Mm-hmm. Where it was easy to get a job was in a school of business administration, because that's where I had a union card, and a union card signed by one of the best in the area, namely Herb Simon. So that turned out to be, I had wanted to come to the West Coast, particularly to the San Francisco area. So Berkeley was excited about getting me and about getting Julian Feldman. Both of us left Carnegie at roughly the same time. The two of us started to teach essentially two things. One was organization theory a la March and Simon, which we both knew from our graduate work, and this new discipline called artificial intelligence, or in some variations of it, computer simulation of cognitive processes. That's when we were having a lot of trouble getting, what would we do? There were no books on the subject. And we just decided that we needed to do a collection. It wasn't just our students who were interested in this. There was a whole nation, or maybe a international need for such a thing. So we took the papers that we had collected up, plus a few more that we asked people to write, and put together a collection called Computers and Thought.
Teaching at the University of California, Berkeley, Feigenbaum and his colleague Julian Feldman published an anthology called Computers and Thought. This became the first bestseller of AI and is still in print as a computer science classic.
In the Computers and Thought book, in the introduction to the AI, the introduction, Ed wrote about similarity, and I'll just read it. Quote, "A useful rule of thumb used by human beings in most of their problem solving is this: attack a new problem by methods that have solved similar problems in the past. The criteria for similarity may themselves be heuristic." Amen.
We build machines to process ideas and concepts and other mental stuff. We make machines that are powered by knowledge. And this was the vision that I heard from Ed, as well as Bruce and others in the Heuristic Programming Project in the 1970s and the 1980s. And it was a very thrilling vision.
Knowledge as stuff is really, you dig it out. That's what leads you to this transfer model, which somebody says, oh, you dig it all out of me, and then I'm obsolete. And as Bruce pointed out, I've strongly believed for years that really what's happening is you're building a partnership. You're trying to help get a system which can communicate with the original person or with other people as a means of communication.
For reasons that are not totally clear to me, I really, really wanted smart machines. I wasn't going to get there by either walking down the road that I was doing with Epams, which is models of verbal learning, or doing what I then considered wonderfully inventive puzzle-solving tasks. But I wanted something bigger, and when I thought of something bigger, I couldn't think of anything bigger in the, and I really still can't, than induction. That is, induction is what we are doing almost every moment of almost all the time.
In 1962, Feigenbaum changed his focus from learning to induction. How were hypotheses and theories formed? By 1964, he sharpened that focus to study induction in scientific thinking. In a chance encounter at Stanford, Feigenbaum met the famous geneticist Joshua Lederberg, winner of the Nobel Prize in Medicine.
When I told him exactly what I wanted about the induction process, it wasn't any old scientific reasoning I was interested in. He said, yeah, I have just the one for you, and we're working on it in our lab. His lab was taking the mass spectra, doing the mass spectrometry of amino acids because they were, their planet probe was going to look for amino acids as part of the method for discovering whether lifelike forms existed on Mars. So the question was, how do you go from looking at a spectrum of an amino acid to the actual structure of the amino acid, the chemical structure of the amino acid? And that's how we started in with the Dendral project.
With Joshua Lederberg, Ed initiated a long-time project in using the knowledge of chemistry plus heuristic search as the organizing elements of a program that interpreted data in analytic chemistry from a mass spectrometer. That was the Dendral program. It was the first attempt ever to automate scientific inference, the first to rely on textbook and experts' knowledge of a scientific domain, and the first to represent such knowledge in an explicit and modular fashion.
The Dendral project, composed of pioneers in AI such as Bruce Buchanan, Georgia Sutherland, Joshua Lederberg, Bill White, and Carl Gerasi, gave birth to the field of expert systems and proved to be one of ED's most ambitious projects. By accurately identifying organic molecules and analyzing their mass spectra, the team was able to create generated hypotheses in chemistry at an expert level.
The basic idea was to develop data structures that captured in a sort of simple way the concepts and rules of inference that experts expressed.
The very simplistic version of saying what the knowledge principle is too simplistic. It's much too broad. I think the right way to use this, and I think this comes from our lineage here, is that it leads to a family of much more specific hypotheses. Each one of them could be falsifiable by experiment.
One of the most powerful generalizations is that the power is in the knowledge.
That was the big idea. And that was, so in my career, that is the huge aha. Oh my God, that's what it is. We were learning how to represent the knowledge of chemistry, and we were learning how to represent it in a very nice way, very high-level symbolic way, where you could actually see exactly what the knowledge was. That didn't bother me at all. I'm a person who believes in building on the scientific results of the past, rather than having to reinvent everything new in your generation. And so I was pretty happy with that, gee, those old ideas really work.
So what is this knowledge principle saying to us then about how these rules make things more powerful? And I think there's three parts to it. First, the world is complex. Second, embedded systems, in order to perform tasks in the world, need to model that complexity faithfully. And third, the more complex a task and its environment are, the more knowledge it takes to model them.
The triumph there was, at the symbolic level, we were able to do something which had been a dream, to kind of come up with a new piece of science that you could actually publish. And, it wasn't special relativity, certainly wasn't general relativity, it was just a little thing that we were able to publish. But still, it was some science.
The discovery that arose from the Dendral experiments was that the main source of intellectual power of AI programs was the knowledge they had of their domain of work, not the reasoning methods they used. The result, Meta-dendral, a program that took sets of knowledge about mass spectrometry and grouped them into theories.
The conception was that you had a problem solver, call it Dendral, that took some inputs and produced an output. In doing so, it used a layer, which I didn't give a name to, but Newell later called the knowledge level, of knowledge that it was using to steer the search and prune the search and so on. That knowledge got in there because we interviewed people. How did the people originally get the knowledge? By looking at thousands of spectra. So we wanted a program that would look at thousands of mass spectra and infer the knowledge of mass spectrometry that Dendral could use to solve individual hypothesis formation problems. We did not have a grandiose vision. This was bottom up. This was really bottom up. We started with the Dendral algorithm, which was the legal move generator, and we started generating some chemical molecules that contained carbon atoms, hydrogen atoms. These experiments amounted to titrating in more and more and more and more and more and more and more knowledge. And the more you did that, the smarter the program became.
I love the Dendral and Meta-dendral work. I view it as foundational and quite in symphony with the more recent work. what was beautiful about the dendral work is this rich declarative representation, the end-to-end nature of the process of doing science. I think that that's a stake in the ground for how we can re-enter and reinvestigate how these methods I've been talking about fit into the bigger picture.
Ed has always exercised immense good taste in selecting problems.
From the successes of the knowledge principle, expert systems also began to expand quickly into other fields such as medicine and genetics, giving birth to the projects Mycin and Molgen.
For years, I had been asking my colleague Josh Lederberg, how come you have been recommending to us that we work in the chemistry or medical areas when in fact you are a geneticist, in fact a Nobel Prize winning geneticist. How come we're not working in your area where you yourself can be the expert? And at one point he said now is the right time. It was a short time after Cohen and Boyer had invented the basic techniques for genetic engineering. And Josh's view was that starts a new era. And if it starts a new era, we can get in on the bottom. That is, if we have to do knowledge accumulation, knowledge engineering, don't start where you have a huge pile of knowledge like in genetics. Start where you have almost no knowledge, which is genetic engineering. That got us into Molgen.
The first computer science project to delve into computational molecular biology, Molgen required storing vast amounts of knowledge from experts around the country.
Since we were connected to this also very primitive thing called the ARPANET via the goodness of DARPA that let our machine on the only non-DoD sponsored machine on the ARPANET, people could dial into so-called tips around the country, which allowed them by phone to access machines on the ARPANET, and we were one of those machines, the machine being called SumX-AIM. AIM stands for AI in medicine. They could come in and use our sequence manipulation routines, which were called SEQ, or SEQ was the name of the package. Before long, we had something like 300 users coming in over the ARPANET to the SumX machine, which at one point was a PDB-10. It later graduated into be a PDB-20, but it never was a major resource. But we had 300 people coming in from biology departments around the country, from pharmaceutical companies that wanted to use this new tool.
With a multitude of projects under his belt, at Stanford, Feigenbaum eventually formed a group called the Heuristic Programming Project. From this, the careers of computer scientists such as Georgia Sutherland, Randy Davis, Mark Stefik, and many others began to bloom.
One way of characterizing a lot of the problems we work on is they're sense-making problems where people are faced with huge amounts of information and need to make sense of them.
The notion that people retire, of course, and you lose them, and you lose the expertise that they have built up over the years. It just sort of walks out the door. And my favorite way to describe this is to explain that this is a fact of life. People build a career accumulating knowledge and expertise, and then they disappear, and everybody accepts this as a fact of life. Well, I think one of the most profound things that happened as a consequence of that research is people understanding that maybe it isn't a fact of life. And the way I like to explain this is to say that this research has changed a fact of life into a solvable problem.
Somewhere in the early to mid 1970s, it occurred to me that essentially one had to change the scale by which AI was being practiced. It was being practiced up till that time by essentially a handful of people. In effect, there was no source book for everything that AI knew. And I wanted to get everything into one piece of work, which turned out to be the Handbook of Artificial Intelligence. It wasn't called the Encyclopedia of Artificial Intelligence. I think there are some reasons why a handbook was a wrong choice of language. For example, Science Magazine would not review it because they never review handbooks, even though it really was an encyclopedia. The way to accomplish this was to harness very large amounts of the smartest talent around, which is Stanford graduate students, and set up a course in which they were reviewing the techniques and methods and history and accomplishments of AI for themselves, but the little packages that they would produce were packages which became chapters or sections of chapters of this volume. Now, the Handbook of AI had an enormous influence. It was everywhere. It was on the Library of Science book list. It was one of those things you would get as a freebie if you joined the Library of Science book list. You could order that as your set of volumes. It sold a lot of copies. It contributed a lot of royalties, the royalty income to the Heuristic Programming Project to fund more research. So it made a big difference in people's decision as to whether to go into the field or not.
Having finished the first textbook for AI, Edward continued to write, highlighting contemporary successes and breakthroughs in computer science.
Just about that time, the Japanese organized a project to essentially do the knowledge-based systems portion of the AI enterprise, but do it in a style different from the style that we were accustomed to in this country. And in addition, in order to get consensus in Japan for such a large expenditure, namely of about $1 billion at the time, and that was a lot of money for 1981, they were going to include parallel computing. So I saw that plan early because I was in contact, by that time I had been in contact with Japanese quite a lot, and I saw that plan early and decided that is really an interesting plan and that is worthy of note. Let's write about that plan. Let's write about the Japanese intentions to essentially close the gap with Americans in computation. And let's do it in a way that talks about our own effort, talks about the successes of the DARPA program, the network, and AI in general, and so on. But I was able to sit down with a friend of mine, a person whose writing I respect a great deal, very old friend of mine, Pamela McCorduck. And Pamela had written a great book on AI, early AI history, called Machines Who Think, now in its 25th anniversary edition. And I was able to convince Pamela to be a co-author, be the writer of this book, sit down and listen to me give these lectures to her, and then let's have lots of conversation about it. So Pamela and I spent dozens, maybe hundreds of hours together, she listening, writing down stuff, asking questions, being a knowledge engineer, bringing the human element into the picture, which of course I as an AI techie would tend to disregard, but she would make sure it's there. And satisfying the key thing about stories. Pamela ensured that we weren't boring, and she really made it an interesting book. It sold a ton of copies. By the time it was finished with its authorized and unauthorized translations around the world, it was about 500,000 copies, which is very big for even books like this that sell 25,000 are thought to be pretty big sellers. That really caught people's attention.
And Ed didn't stop writing. Soon after the fifth generation, Feigenbaum was hard at work on his next book, The Rise of the Expert Company.
Peter Hart, one of the early pioneers of AI, Peter said, how about doing a series of case studies of excellence in expert systems? I took Peter seriously and got going on that. The Rise of the Expert Company. What we did was find great stories of companies that had been applying AI. For example, the IBM effort to apply expert systems. Configuring computers, mini computers, was another one of the stories. DuPont's different approach, led by Ed Mahler, a DuPont chemist, to do Mahler had the idea that you didn't really need $10,000 pieces of software and $10,000 mini computers. What you needed was smaller pieces of software and personal computers, and make the individuals in the company their own knowledge engineer. They didn't need a knowledge engineer. They're smart enough to be their own knowledge engineer. Give them the right tools.
When I got to the technology of expert systems, it was the only technology that I developed. I could not tell whether it was ready or whether we could use it. So that created the Skunk Works and ultimately created the activity in DuPont. If we could turn the developer into the knowledge person himself, the cost of that's what it costs to train him on how to use the tool. Just like it costs you to train him to use Excel, we could train him to use a tool that would be suitable. That essentially led us down the path of the systems that could economically address a $100,000 problem.
Now, one of the beautiful things about Ed is that he has several, and has always had several high-level goals working at the same time, often collaboratively. I mean, he cares about science and truth in the scientific sense, other kinds of truth. He also cares about things working socially, about how a business can make money. For me, I don't care so much about money. We have a different balance. But he runs these things together and collaboratively, which I think is one of the reasons he's been so thoroughly successful.
One of the things that's always fascinated me about Ed was his irrepressible optimism. He constantly sees the possibilities and is enthralled and inspired by them. And I have to say, coming back here today, I have felt that again, and it's a wonderful breath of fresh air.
By that period of time, the head of steam that we had built up over parallel computing was kind of spent, and it was necessary to both renew the DARPA application for more research in parallel computing and invent some new ideas. I had run out of gas on writing DARPA proposals. There's a time when that's appropriate and a time when you've had enough of it in your life and you just don't want to do it anymore. And so I told a group, most of you are highly prestigious senior scientists in your own right. Write the proposals for what you want to do, and I'll be the PI for them. But I don't want to write those proposals. Well, within 1 year, I had lost Harold Brown to go to Hewlett-Packard because he didn't want to, HP Labs because he didn't want to write any proposals. Within 2 years, I had lost Penny Nee because she didn't want to write any proposals. Barbara Hayes Roth did stick around writing proposals, and she did, in fact, do several interesting things thereafter. But what it amounts to is that with this lack of sustained funding, the lab was kind of falling apart. This team effort was falling apart. So there I was. When the phone rings, and it's Professor Sheila Widnall of the Department of Aeronautics and Astronautics of MIT, and she called me to ask if I knew of anyone who was interested in filling the job of chief scientist of the Air Force. I thought about it, briefly discussed it with my wife because it involved a move to Washington, and called back Sheila and told her, yes, I was interested in doing that.
And then there's a duty to one's country, and Ed has done that. He was the chief scientist for the Air Force for 3 years, and that must have been quite an experience.
Transitions into the government take a certain point of view. Not everybody is so motivated from youth to go into that. There are people in this room that, I know have said to me, gee, all my life, I thought I wanted to be a professor at some university, and I just haven't even been thinking about government because it hasn't been on my radar screen. And yet other people at some point in their career see it as a really viable option.
But I had this kind of upbringing of respect, integrity, honor, duty, those kind of things. We could have been Marines, Ed. Ed had that same kind of upbringing. Integrity, all scientists have a high degree of integrity and integrity to their profession. But there's also integrity to oneself, which is very important. Ed has had that really important quality all these times.
My job was to be a window on science for the Chief of Staff of the Air Force. If anything important came up, to point them in the right direction, to do liaison with the Scientific Advisory Board of the Air Force, which is a high-level group of 60 excellent volunteers that do studies for the Air Force, to do liaison with other science establishments in Washington, like the National Science Foundation, director and staff, the Commerce Department's Assistant Secretary for Science and Technology, to do visits to lots of Air Force bases to find out what's really going on. In fact, my first Chief of Staff that I worked for, before they changed, was a guy who told me, I want you out of this building as much as possible. You don't learn anything in this building. That's the Pentagon. And basically he was right. You don't learn anything in the Pentagon. You have to really go outside to do the job right. So I spent a lot of time on the road. The Army had actually established an expert systems center in the Pentagon. So I was able to go down to the basement of the Pentagon and actually help them with specific projects, look at what they're doing, recommend things to them and to the Air Force. I was able to do things jointly with the Navy as well. I just found it a terrific opportunity, and it was very interesting to be inside the Beltway.
In 1995, Ed Feigenbaum received an award that honored his contributions to artificial intelligence. Jointly with Professor Raj Reddy of Carnegie Mellon University, Feigenbaum received the 1994 ACM Turing Award for pioneering the design and construction of large-scale artificial intelligence systems and demonstrating the practical importance and potential commercial impact of AI technology. The award is considered the highest distinction in computer science and is sometimes called computer science's Nobel Prize.
I'm waiting, maybe we're all waiting, for the Principia Mathematica or the origin of species or something like that that's going to really set this field in motion, because a lot of the really basic questions here we're still fumbling with.
We need to be talking not just about a goal, a single goal, but the way we have and the way children have of having lots of goals and adaptations all at the same time. They sometimes conflict, they sometimes support each other, they sometimes are confusing, and we don't use them all at the same time. And what we are trying to do governs very much what kinds of notions and how we learn things.
It seems to me there are a couple of useful places where we might look for additional ideas in moving forward toward our grand goal of reaching this summit in the mountain climbing sense. You know, the peak is still there. A lot of us are, I think, still very impressed with these tools that can be applied to chemistry, biology. We're helping the people in the green valleys, but meanwhile, the summit's still there. So, you know, after we sharpen the tools in these green valleys, let's move on toward the summit.
I think many of the heuristics that we focused on are, in some sense, one level below that. They're more on the conceptual level, heuristic formulations of ideas, of meanings. But the idea of formulating different kinds of similarity and which ones to use when, I don't think we've come near to working on hard enough.
When you're faced with a complex problem, you don't give up saying this NP complete. You find an approximate or satisfying solution that's good enough. So we human beings, are happy with good enough solutions.
What I like about the methods of building human machine systems and being able to watch people act inside them is the capacity to learn something from human behavior. I mean, we're still the best examples to look at. And when you can get more and more detailed traces, as I call it, exquisitely detailed traces of people who are generating not just new knowledge, but actually redefining new search spaces within there, I think that takes us to all kinds of levels that we don't really talk about.
In my view, the thing that we call AI, or that maybe is better called computational intelligence. computers doing intelligent things is the manifest destiny of computer science. That is the end of the road. That is, if you're going to use the, which I love to do, the Lewis and Clark metaphor of starting out of St. Louis and slogging your way through the Missouri Valley and up the mountains to wonderful places that are difficult to achieve, the goal is the ocean. And AI is the goal. And you can stop along the way. You can have a wonderful life in Salt Lake City doing whatever, graphics, or you can stop in Denver and do databases, but the goal is AI. Now, AI has a tendency to spin off little things that sit in valleys. For example, if you look in Computers and Thought, Oliver Selfridge had a key paper, he and Deneen had a key paper on distinguishing X's from O's. That was the birth of optical character recognition. By 1964, that is 1 year after Computers and Thought came out, optical character recognition was its own named field. And that has happened time and time and time again in AI, computer vision, expert systems, computational linguistics.
The scientific quest still remains for an understanding of the processes of thought. Scientists and engineers continue to create and use models based on the work of Feigenbaum and his colleagues. How do we reason? How do we form new ideas? How do we acquire knowledge and learn? These are questions that may take a long time to answer, but artificial intelligence continues to make progress in these areas, forging new ground and discovering new possibilities.
Meta-dendral and with the follow-on done by Tom Mitchell for his thesis called Version Spaces, represented a milestone for me, a milestone on the path that I had intended to be on all along, namely the path toward the future of machines that would produce scientific theories for mankind. And I still believe in that path. I still would like to be on that path. If I had another career, I would still be on that path. The most effective way to make progress on the ultra-intelligent computer, which happens to be my engineering slant in this whole game, is to study the way people behave. We have excellent examples of intelligence walking around us all the time. They're easy to study. There are billions of them to study. And we, as scientists, in my view, at least for myself, and I'm pretty sure it holds for most of AI, we're better at discovering things than we are at inventing things. Inventing is hard. Finding mechanisms by discovery, looking at complex human behavior and modeling that behavior is easier. As soon as we uncover principles from human intelligence, we can improve upon those principles. There are a number of significant ways in which we differ from animals, but one way is that we transmit our knowledge via cultural mechanisms called texts. It used to be manuscripts, then it was printed text, now it's electronic text, but we put our young people through a lot of reading to absorb the knowledge of our culture. And to boil it down to some bumper sticker language, you don't go out and experience chemistry. You go out and you study chemistry. And we need to have a way in which computers can read books on chemistry and learn chemistry, or read books on physics and learn physics or biology or whatever. We just don't do that today. Everything is handcrafted. Everything is knowledge engineering. The human mind transforms it into symbolic expressions. We'll be forever doing that unless we can find out how to read from text. That our group, the HPP, did path-breaking work in a large unexplored wilderness, but that most of that beautiful wilderness today remains largely unexplored. When we finish our job, we will have invented the ultra-intelligent computer. That's what we're trying to do, whether it's 100 years from now or 200 years from now, but that's what we're trying to do.